When you stand on the ground, the physical world is visually overwhelming. Human vision is strictly bound by the horizon, making it impossible to comprehend massive mountain ranges, sprawling forests, and vast oceans all at once. To understand the whole board, we have to step back, way back. But holding the entire planet in your field of view doesn't help you build a road, plot a maritime route, or measure a national border. We need a way to capture this massive, three-dimensional reality and compress it into something we can actually hold and use. The solution is the map, a representation of the Earth's surface, or a specific part of it, drawn on a flat surface. Transferring a rugged globe onto a flat piece of paper involves heavy data compression. To ensure that flattened image remains perfectly accurate to the real world, cartographers rely on 3 strict rules of translation. The first tool is scale. You obviously cannot draw a 100-mile highway on a 100-mile piece of paper. Scale establishes a strict mathematical ratio between the drawing and reality. If a map has a scale where 1 centimeter equals 1 physical kilometer, every distance on that page shrinks in exact proportion to the physical Earth. This specific, measurable ratio separates a scientifically accurate document from a hand-drawn sketch. But a perfectly shrunken world is useless if the user doesn't know their orientation. That requires the second tool, direction. To standardize navigation, cartographers establish strict orientation parameters, placing north at the top of the page. By locking the top edge to the North Pole, every other direction, south, east, and west, falls into place, anchoring the paper directly to the physical rotation of the planet. Together, scale and direction provide a mathematically sound, physically oriented foundation. They give us a blank canvas that strictly mirrors reality. Now we have to fill that canvas. If you draw every single tree, hospital, and river exactly as they appear in real life, the page quickly turns into an unreadable, chaotic blur. To solve this physical clutter, mapmakers use their third tool, conventional symbols. Complex, three-dimensional objects are stripped down to simple, efficient icons. A massive medical facility becomes a crisp red cross. A sprawling forest reduces to a flat green tree shape. Intersecting railways become a clean, dashed line. Because these specific symbols are agreed upon globally, they form an international visual language that anyone can read, regardless of local dialects. Symbols strip away the visual noise. They compress massive amounts of geographic data, so humanity can assess an entire region at a single glance. Once you have a system that scales, orients, and simplifies the physical world onto a 2D surface, you gain incredible leverage over your environment. Administrators can define national borders and measure vast distances between cities without ever having to walk them. Military leaders can plan troop movements across terrain they have never personally seen. In high-stakes situations like a flash flood or an earthquake, maps give emergency response teams an immediate spatial layout of the disaster zone, allowing them to route critical resources precisely where they are needed. Today, the primary medium has shifted from parchment to digital code, but the underlying cartographic engine remains untouched. Early handheld GPS units still processed raw satellite data by plotting coordinates along strict directional axes and representing landmarks with tiny pixelated symbols. Even the mapping software we use daily to navigate traffic or find a restaurant relies entirely on that exact same trinity of scale, direction, and symbols to render the planet on your screen. Maps serve as mathematical decoder rings. They prove that to navigate something as impossibly large as the Earth, you first have to figure out how to shrink it down.